Have you ever thought about like those ancient Roman buildings?
Yeah.
The ones that are still standing after like what, 2,000 years?
Oh, yeah, absolutely. It's incredible, isn't
It
it?
really is. And I was thinking about the Pantheon in particular. That dome,
Oh, yeah. That's a classic.
built around 126 AD. Can you believe that?
That's mind-boggling.
Get this, it's still the largest unreinforced concrete dome, like in the whole world. It weighs something like 4,463 tons. That's just wild.
And it's still holding strong.
Right. That's what I'm saying. How has it lasted for so long without cracking? Especially compared to some of the stuff we build these days.
Yeah, that's the big mystery, isn't it? Like, what was their secret? Why does ancient Roman concrete seem to be so much more durable?
It makes you think, maybe they knew something that we're only now starting to figure out.
Totally. That's exactly what we're going to be looking at today, the incredible staying power of ancient Roman concrete. And why it seems to outlast so many modern structures. It's like almost a bit humbling, you know?
Absolutely. We think we're so advanced, but then you have something like the Morandi Bridge collapse back in 2018.
Oh, yeah, real tragedy.
It was a major bridge in Genoa, Italy, like a crucial link for transportation, designed by Riccardo Morandi.
Right, a renowned engineer.
Yeah, and the bridge was completed in 1967, a cable stayed design, so, pretty modern for the time.
And it had this like really innovative design feature. They encased the steel cables that held up the bridge in concrete. The idea was to protect them from corrosion.
It makes sense, right?
Yeah, you'd think so.
Right.
Reduce the need for all that constant maintenance and make it last longer.
But then, sadly, on August 14th, 2018, during a big rainstorm, a really bad one, two of the main support pillars, numbers 9 and 10, they just gave way.
Yeah, it was awful.
A huge 80-meter section of the bridge, the roadway, it all just plummeted down. 43 people lost their lives.
Really brings home how, even with all our modern technology, things can still go terribly wrong.
It does. It's a reminder that even the most advanced engineering can have some pretty serious vulnerabilities. And when the investigators looked into what caused the Morandi Bridge to collapse, it was water.
Water. Yeah, it's incredible how destructive something so commonplace can be.
It really is. What happened was water seeped into the concrete that was supposed to be protecting the steel cables. And, steel and water, not a good combo.
Corrosion is a real nightmare for steel structures.
Exactly. And that's what happened. The steel started corroding. And when steel corrodes, it doesn't just rust away, it also expands. Those corrosion products take up more space.
Right, like iron oxide, it's much bulkier than the original steel.
Exactly. So that expansion put pressure on the concrete. It cracked, which just let in more water, starting this vicious cycle. And eventually the cables just snapped.
Under all that stress from the traffic and the weather, it just reached a breaking point.
So, yeah, it's a pretty sobering example of how water can undermine even really sophisticated structures.
It really highlights the contrast with Roman concrete, doesn't it?
It does. You have a modern bridge using all these cutting-edge techniques collapsing in just a few decades. And then you have something like, let's take Caesarea Maritima, for example.
Oh, that's a great word.
An ancient Roman port city near what is now Haifa in Israel.
And not just any port, a major one. A real hub of Roman activity.
Right. And this wasn't some sheltered harbor. They built this right on the open Mediterranean. Can you picture that? Those waves constantly pounding against the harbor for centuries.
Absolutely. Those waves on the Med can be pretty ferocious.
And think about the traffic, ships coming and going, loading and unloading, all that wear and tear.
And yet, significant portions of it are still standing today.
Thousands of years later, those concrete blocks they used to build that harbor, they're still there, submerged beneath the waves. It's incredible. So on one hand, you have a modern bridge designed with all this advanced knowledge, succumbing to water damage in just decades. And on the other hand, you have an ancient harbor constantly exposed to the Mediterranean, still standing after millennia. Makes you wonder what their secret was.
It really does. And there's growing evidence that a lot of it comes down to their concrete, specifically the mortar they used to bind it together.
Yeah. There's actually this ancient note, like a written record, dating all the way back to 79 BCE. And in it, they describe Roman mortar. Get this, they called it a single stone mass, impregnable to the waves and every day stronger.
Every day stronger? That's a pretty bold statement, right?
It is. Most materials, especially when they're constantly exposed to water, they break down, they weaken, they crumble. But the Romans are saying their concrete actually got tougher thanks to the water.
It almost sounds like something out of science fiction, doesn't it? Like self-healing concrete.
Right. Imagine concrete that could repair its own corrosion.
So the question is, how did they actually do it? How did they create this seemingly magical concrete?
Well, I think the answer might be hidden in the geology of Italy itself.
Oh, interesting. You're talking about the volcanic activity.
Exactly. There's this city, Pozzuoli. It's in southern Italy. It has these amazing Roman ruins, but it's also right in the middle of a very volcanically active area.
The Phlegraean Fields, right? Known for its calderas and...
Yeah. And it's not just ancient history. Back in 1982, things got pretty real in Pozzuoli. The ground started rising, and I'm not talking about a few centimeters. It rose 2 meters in just 2 years.
Wow, that's a lot. I can imagine that caused quite a stir.
It did. People were freaking out. They thought a major volcanic eruption was imminent. 40,000 people had to evacuate. But nothing happened. No eruption.
So what was going on?
Well, scientists had to figure that out, right?
Yeah.
So they drilled down deep beneath the surface, and what they found was a layer of carbon-rich material way down, about 2.9 kilometers below the city.
So something was happening down there.
Right. It turns out that when seawater seeps down into that layer, it reacts with the carbon-rich material.
Ah, producing carbon dioxide gas.
Yep. And that CO2 then reacts with, other stuff in the surrounding rocks, calcium, hydrogen, all that chemistry going on deep underground. And one of the things that gets created in all those reactions is, you guessed it, hydrated lime.
And hydrated lime is, of course, a crucial component of...
Roman mortar. Exactly. Now, this geothermal activity beneath Pozzuoli, it's like this constant upward force. It pushes the newly formed lime closer to the surface.
Where it encounters
volcanic ash. From all of the past eruptions, these layers of ash. And that's where it gets really interesting. When that lime and volcanic ash mix, they form this super strong caprock.
Caprock, that's the really dense rock layer you often find.
Yeah, on top of geological formations. And in this case, this incredibly strong caprock, that's what actually stopped the volcanic eruption from happening. It was like this natural pressure valve.
So the same geological forces that were causing all this panic, they were also creating the ingredients for incredibly strong building materials.
And wouldn't you know it, the Romans called this stuff pozzolana.
Named after the city itself.
Right. It's like, come on. You're living in this area, you see this super strong material forming naturally, and you're trying to build stuff that lasts. Of course they're going to use it.
It seems almost too perfect, doesn't it?
It does. It makes you wonder if they fully understood, the science behind it, or if it was more of a, hey, this stuff works really well.
Well, to get a better understanding of that, scientists decided to get up close and personal with some actual ancient Roman mortar. They took samples from a city called Prevenum. It was inhabited as early as the 2nd century BC, so this concrete is pretty representative of what they were using back then.
So how do you analyze ancient concrete? I'm picturing scientists in lab coats with high-tech equipment.
Pretty much. They used a technique called SEM-EDS. It's like a super powerful microscope that can not only show you the tiniest structures within a material, but also tell you exactly what elements are present. And what they discovered was the way the Romans made concrete, it was quite different from how we do it today with our modern Portland cement.
Oh, really? How so?
Well, their first step was creating quicklime. They did this by heating up limestone to crazy high temperatures, like 900 degrees Celsius.
That's hot.
It is. And that process releases carbon dioxide as a byproduct. Kind of a parallel to what was happening naturally underground in Pozzuoli, wouldn't you say?
Yeah, it's like the same chemistry, just happening in different places.
Right. So after they got their quicklime, they mixed it with stuff like pozzolana, that volcanic ash. But here's the thing. They did this mixing at those same high temperatures. That's a big difference from how we make Portland cement today, which is usually at much lower temperatures.
Okay, so that high temperature mixing, that was a key part of their process.
It was. And because of that, they ended up with these little bits of unreacted lime still in the mix, like little pockets of it. They're called lime clasts.
Okay, so it's like leftovers.
Kind of, but they're actually incredibly important.
How so?
Well, when they added water to the mix, the quicklime would hydrate, react with the water, and that would form calcium hydroxide.
Right, and then
that calcium hydroxide would react with the silica and alumina that were in the volcanic ash. This is the big one, the famous pozzolanic reaction. And the result of all that chemistry, a super strong, super stable compound called calcium aluminum silicate hydrate. Or, we can just call it SCASH.
cash. So CH is what makes Roman concrete so strong. It's like the glue that holds it all together.
Exactly. Think of it as the superglue of ancient Rome. And over time, that pozzolanic reaction could even lead to the formation of some incredibly rare and strong minerals, like altobermerite, for example.
Wow. So it's not just strong, it gets even stronger with age.
Pretty much.
That's amazing. And I bet this explains why structures like Caesarea Maritima are still standing. That constant exposure to seawater, it actually helped create those super strong minerals.
Right. The seawater wasn't an enemy, it was part of the process. It's the opposite of what happens with most modern materials. They degrade over time, especially when they're constantly wet. But Roman concrete, it actually benefited from that exposure.
That's so cool. So thinking about all of this, we know that modern concrete, specifically Portland cement, it's, kind of a big deal. It's what we use to build pretty much everything.
It's ubiquitous.
Right. But it's also a huge contributor to global emissions. Like I read somewhere that Portland cement production accounts for around 8% of all carbon emissions worldwide. That's massive.
It's a significant environmental burden.
Exactly. And we were talking about how Roman concrete, it seems like it could be way more durable. And scientists are saying that using Roman concrete methods could actually help reduce those emissions.
Yeah, that's the exciting prospect.
So if Roman concrete is potentially so much better for the environment and it lasts way longer, why aren't we using it more?
Well, it's not quite as simple as just switching back to ancient Roman recipes. There are a few reasons. First off, until recently, we didn't really understand exactly what was going on with Roman concrete at the, molecular level, like the specifics of those chemical reactions, the long-term mineral formation, all those things that contribute to its durability. It's only in the last few decades that we've really started to unravel the science behind it.
Makes sense. If you don't fully understand how it works, it's hard to, replicate it reliably.
Exactly. Another thing is availability. High-quality natural pozzolana, it's not like it's just lying around everywhere.
Yeah, volcanic ash, right.
Right. So using it on a large scale, that's going to be a challenge. And while we know that Roman concrete works incredibly well in certain applications, especially in marine environments, we still need to do more research to figure out how it performs under all the different conditions we use concrete for today. The Romans didn't leave us detailed instructions. We're still figuring out the best mix ratios, the optimal construction techniques, all those practical things.
Oh, that's a good point. It's not like we have their blueprints.
Exactly. It's a puzzle we're still piecing together. But it's really encouraging to see that some modern construction projects are actually starting to incorporate Roman concrete techniques. Testing the waters, seeing what's possible.
That's really cool to hear. It's like we're looking back to the past for solutions to some of our most pressing problems today.
It's a great example of how sometimes ancient wisdom can be incredibly relevant to modern challenges.
It is. So to wrap things up, it seems like the secret to Roman concrete isn't just one single thing. It's this really cool combination of materials and chemical reactions. That pozzolanic reaction between the quicklime and volcanic ash, activated by water, it leads to self-healing properties. And over time, it creates those amazingly durable minerals, especially in places where the concrete is exposed to seawater. Like it's the exact opposite of the Morandi Bridge, where water was the enemy.
Exactly. With Roman concrete, the water is almost like an ally. It helps the concrete get stronger. And if we can fully understand and, recreate those ancient Roman techniques, it could be a game changer. Imagine being able to build structures that last for centuries with a much smaller carbon footprint. It's a conversation that's only just beginning.
It is. And it'll be really interesting to see where it goes. So that wraps up our deep dive for today.
Thanks for having me. It was great to chat about this.
It was my pleasure.